Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Mr. Shong, and this lesson is brought to you by the Gauteng Department of Education in collaboration with the Saipono Discovery Center. All right. Today, good people, we are looking at probability. Okay. We are going to be looking at revision of concepts that were studied in grade 10 and 11 in particular. Okay. Right, let's look at our objectives for today, or lesson objectives. By the end of this lesson, you should be able to define probability. That's a very important definition, okay? And then to understand the meaning of the concepts, mutually exclusive events, exhaustive events, and complementary events. And then you need to know and apply the probability identity. And then you need to understand the meaning of independent events and solve numerical problems involving events that are independent. Then you need to know how to use the probability tools, your Venn diagrams, your tree diagrams, and your contingency table. You should know how to use all of those to solve probability related problems. All right. Moving on. Obviously, this you should also know that you can get this on CAPS on page 42 and also on the exam guideline that was published in 2021 on page 6. Okay, prior knowledge. What is the knowledge that you should have, that you should bring into this lesson? It's the definition of probability, Venn diagrams, mutually exclusive events, outcomes, exhaustive events, equations, and the product rule. So that is the knowledge from earlier grades. All right. Now, as our baseline assessment, I need you to define these following terms as you understand them in the context of probability. So I'm just going to give you 3 minutes, just 3 minutes, just to talk about these 4 terms here. Just 3 minutes, and your 3 minutes time starts now. Hello and welcome back. Remember, we are available on our WhatsApp interactive number 079-578-2908. We are available there. If you have any questions based on today's lesson, you can actually interact with us there. All right. Okay, let's move on. I want us to look at the solutions to this questions here. Number one, outcomes. Outcomes refers to the result of each trial. Is called an outcome. So the result of any trial that you have in probability, you call it an outcome, or different ways an experiment can turn out. If you are experimenting, whatever you get out, that's an outcome. If a coin were tossed, the outcome would be a head or a tail, all right? So that's outcome. Sample space is the list or a set of all possible outcomes. So if you cluster all those outcomes that are possible in any possibility, then you have that would denote your sample space. And then an event is a subset of the sample space that consists of outcomes that satisfy a particular condition. So out of the sample space, you can select outcomes that would represent a particular condition. Like for an example, if you are rolling a six-sided die and you say you are interested in even numbers, so what you are interested in would be the event. Those are even numbers. That is a subset of the sample space. Remember, the sample space has numbers 1 to 6, so that subset that you are interested in would be 2, 4, 6. Those would be your even numbers. So it's a subset within that particular sample space that would satisfy a particular condition. And then probability is the likelihood of an event occurring. What are the chances that this particular event would occur? All right, let's move on. Defining probability, that's where we start. All right, we define probability as the chance that something would happen or the likelihood of an event occurring. How likely will that event happen? Sometimes we can measure probability with a number like a 10% chance of rain. All right, that's what our weather forecast tells us, that there would be the 10% chances of rain. All right, or you can use the words such as impossible, unlikely, possible, even chance, likely, and certain. So those are some of the words that you can use to show how probable an event is to happen. If all possible outcomes are equally likely, then we can calculate the theoretical probability of the event as follows. Probability of an event, E, as number of elements in the event divided by number of elements in the sample space. All right, so that is theoretical probability. But remember, we also have the experimental probability that takes into account also issues of relative frequency. All right, let's look at the probability scale. All right, you can see it's a scale from 0 to 1, where 0 represents impossible and the possibility increases as you go to certainty. So you can see here it's unlikely that it would happen, but it's not impossible. All right, but it's very unlikely. It's unlikely that it will rain during winter. It is possible. It is not impossible, okay? But it's very unlikely, all right? And then an even chance, if you are tossing a coin, it is there is an even chance of getting a head or a tail, all right? It's either you get a head or a tail, so we have even chances. And then we have likely, something that is very likely to occur. It's not certain, but very, very likely. All right, and then we have certain. All right, certain, it means no matter what can happen here, we are certain that tomorrow would be a Thursday, so that is certainty there. All right, and then from there we are looking at an important note here. The probability of 0 is impossible, and an event with a probability of 1 is certain. All right, and then the probability is trapped between 0 and 1 for any event A. All right, let's move on. Let's get into the first tool, probability tool, which is the Venn diagram. All right, Venn diagrams are used to show how events are related to one another. Venn diagrams can be helpful when you encounter problems where you need to calculate probabilities. All right, a rectangle is used to denote the sample space. However, any closed shape can be used. Usually circles would represent the event within the sample space. Any closed shape can be used there. And within these events, we can denote three things here. Either the number of elements in that particular event, A, or the number of elements in the event B. You can also talk to the probabilities in event A and probabilities in event B. You can also list the elements that are involved, the list of elements that are involved. So those are the types of Venn diagrams that you have. You have a Venn diagram for listed elements. You have a Venn diagram for number of elements. You have a Venn diagram for probabilities. But remember, if it's a Venn diagram for probabilities, you should also remember that this Venn diagram can have probabilities expressed as a fraction, all right? Can have probabilities expressed as a decimal, all right? Can also have probabilities expressed as a percentage, okay? So those are some of the things that you need to know, right? Just like I said, we have three types of Venn diagrams. Venn diagrams with with listed elements, Venn diagrams with number of elements, Venn diagrams with probabilities, all right? And you can also have, apart from that, you can have the shaded Venn diagrams where we are going to shade a particular region that we are interested in, all right? Venn diagrams now, intersection, let's look at the Venn diagrams to explain some of these probability terminologies or concepts. Intersection, when we talk about an intersection in the context of probability, we are going to be using AND, all right? AND means intersection. Remember, AND in probability and AND used in our ordinary language, English, is not the same, all right? In probability, if we say AND, we are talking about the intersection, only elements that are common to both sets, all right? So here we are saying, as an explanation, the intersection of event A and B is an event consisting of common outcomes that are in A and B. So you can see that here there's a shaded area there. The shaded area represents the intersection, all right? And then we have the union, all right? The union is sometimes we use or for the union, not like in your ordinary language where or would mean you take this or that, all right? But in probability, when they say or, it means you are taking all those elements that are involved there. So you are unifying both the sets. That is why at times we refer to this as the union. You unify the two sets if it's two sets that you have there, okay? So the union A and B is an event consisting of all the outcomes that are in A or in B. All those outcomes there are representative of the union, all right? And then let's look at Venn diagrams still to explain this concept of mutually exclusive events. These are events that cannot occur at the same time, all right? So these are events in the context of Venn diagrams that do not have an intersection, okay? So you can see here this, the sets are disjoint, all right? The sets are disjoint. But when you talk to inclusive events, then we talk to events which have common elements. So you can see here that they are joined here by what? By the intersection, which is a total number of elements, which is 4 there, all right, in the intersection. So that's what we are actually looking at when we talk mutually exclusive events. They cannot happen at the same time. There is no intersection, which means that the probability of A and B is equals to 0. So once you can calculate the probability of the intersection and you get that it's equals to 0, then you know that those events are mutually exclusive. But if the probability of A and B is not equals to 0, then you know that these particular elements are not mutually exclusive, but they are rather inclusive, all right? Let's move on. Still on our Venn diagrams, we want to look at the concept of the exhaustive events. All right, we use Venn diagrams to explain the concept of exhaustive events. They cover all elements in the sample space. I'm using an example here. When you roll a six-sided die, your outcomes would be 1, 2, 3, 4, 5, 6. When you roll that die, you can get any of these numbers. All right. So if you check here, we have 1 in the sample space, we have 1 in the Venn diagram, we have 2 in the sample space, 2 in the Venn diagram, we have 3 in the sample space, 3 in the Venn diagram, 4 in the sample space, 4 in the Venn diagram, 5 in the sample space, or within the given events in the sample space, we have 5 there. We have 6 in the sample space, and 6 is within the given event. So you can see that there are no event or elements that are outside our defined event. So we say that because there is 0 element outside, then the events exhaust the sample space, okay? Because all the elements that are in the sample space are elements that are in the event, okay, A and B. There are no elements that are outside. So the events A and B exhaust the sample space, all right? And then from there, we are looking at only events, all right? Only events. When we are looking at only events, we are looking at an event that represents the element that are in that specific set. If we are saying P only will show elements that are present in set P only. Note that the intersection is also excluded. We are excluding this area here because we are saying P only, because this area here represents what? P and Q. All right, represents P and Q. All right, let's move on to mutually exclusive events. We've explained them in the context of Venn diagrams. Let us talk to it again here. These are events that cannot happen at the same time. The occurrence of one event excludes the possibility of another one occurring. Examples of mutually exclusive events: Elena cannot be in Gauteng and in Western Cape at the same time. That is impossible for you to be in 2 geographical locations at the same time. So we say the 2 are mutually exclusive, okay, within the sample space of the provinces that are in South Africa. All right, so it should be between, you should be talking to these mutually exclusive events in the context of a particular sample space, okay? And then Elena cannot be in grade 11 and grade 12 at the same time. So within the sample space of the schooling system in South Africa, we cannot have Elena being in grade 11 and grade 12 at the same time, all right? So these are 2 events that are mutually exclusive, all right? So the Venn diagram shows events that are mutually exclusive. You can see the sets are disjoint. We spoke about this earlier. We spoke to all of this earlier on, okay? And then the Venn diagram shows 2 events that are not mutually exclusive, all right? You can see that these events are inclusive here. The probability of the intersection is not 0. I think I've made reference to that as well earlier on. All right, the probability identity, very, very important. It is sometimes referred to as the general addition rule, right? This is the rule that we use in probability. It says the probability of A or B should be the probability of A plus the probability of B minus the probability of A and B. That is general, all right? That is the general addition rule. But if events are mutually exclusive, then the probability of the intersection is equals to 0. Then we can now alter the general addition rule. We can make amendments to the general addition rule. Where we see the probability of A and B, we put 0 because we know that the events are mutually exclusive. So that we get that this would be the general, the addition rule. This would be the addition rule for mutually exclusive events. This would be the addition rule for mutually exclusive events. So those are the things that we are actually looking at here, right? Let's move on. The exhaustive events, I think we've also made reference, we spoke about this, but let's get into more detail as far as this is concerned. The exhaustive events are events that contain all elements in the sample space within them. You remember I said they exhaust the sample space. So if the sample space has 10 elements, the 2 events that you are talking to, or the 3 events, will have all those 10 elements that are in the sample space. So the events exhaust the sample space, okay? There are no elements in that are outside. In Venn diagrams, events are exhaustive if there are no elements outside the defined events, all right? The elements would be in the sample space, but will not be in the defined events, all right? That's what it means if we say there are no elements outside. In the example below, A and B are not exhaustive because of this element 1 there, which is within the sample space but outside of the defined events. So the events themselves do not exhaust the sample space. Remember, when you say exhaustive, you are saying exhaustive events. So the events themselves must exhaust the sample space. These 2 events, A and B, do not exhaust the sample space, all right? Because there's one element number 1 which is outside of the defined events but within the universal set, all right? So both mutually exclusive events and inclusive events can be exhaustive if the probability of A or B, all right? If the probability of A or B is equals to 1, or the probability of A plus that of B is equals to 1, so they can be exhaustive if that is the case there, all right? Now, moving on to the complementary events. Now, we are looking at the complementary events in 2 different ways to say if events are complementary, they should be satisfying the following conditions, all right? They should be mutually exclusive and they should be exhaustive. Then we say that they complement each other. To say whatever that is not within this particular event, we are definitely sure that it is contained in the other event. All right, but remember, they must be exhaustive. All right, they must be exhaustive. So we are saying events that cannot occur at the same time. And if event A occurs, then the complement of A is not A. Whatever that is not in A should be contained in the other event. All right. So the events A and B and its complement not A or the events A and its complement not A are mutually exclusive. They cannot happen at the same time. All right, but they are also exhaustive. They are also exhaustive. All right. So when events are complementary, the event either happens or does not happen. That is why we have not A. It is certain that they will happen or not happen. PA plus the probability of not A is equals to 1. Because remember, we said they are mutually exclusive. All right. Another way is to say that P not A is 1 minus the probability of A, or P probability of A is 1 minus the probability of not A. Complementary events can be shown in the Venn diagram there. You can see the Venn diagram there. All right. To prove that events are complementary, we need to show that the events are mutually exclusive. The probability of the intersection is 0, and to show that they are exhaustive, the probability of the union is equals to 1. All right. So we are bringing in these lots and lots of terminologies, but if you understand it, then you will understand probability. It is more about the understanding of the terminology, and then the maths will come after. All right. The maths will come after. Okay. Now let's look at Venn diagrams with 3 sets, all right? Venn diagrams with 3 sets. If you are looking at 3 sets, can see when we start filling these Venn diagrams, we work from the inside out, okay? So in that particular area that I've blocked there, it is the probability, it is the space or the area that represents the intersection of all the elements A, B, and C, if you have 3 Venns, okay? And then here we are talking about B and C only. And then here we are talking about A and B only. And then here we are talking about A and C only. All right? And then from there, when we go outside, we're looking at B only, C only, and A only. And then here we are going to look at whatever outside the events. We are going to look at the elements that are not within the given events. All right. Okay. Let's move on to the methodology. The methodology for drawing Venn diagrams with 3 sets. How do we draw Venn diagrams with 3 sets? We can follow the 4-point approach, the APO approach, all right, which explains how we should complete. We first complete for all right? That is the intersection of all events, all right? That is where we start. And then we work with the pair. That is the intersection of 2 events. And then that's where we need to subtract the 1 for 3 because it has already been counted, unless if they said only, all right? And then we complete the individual. So we are working from the inside, we are going outside. That is what the APO approach is saying. Work from the inside and then gradually go to the outside, all right? So we complete the individual and then lastly, we complete the outside, all right? Which means at the end, you need to go back to your Venn diagram, add everything in the events and check whether the sum of everything in the events is the same as the number of elements that you should be having in the sample space. If it was a Venn diagram for number of elements. But if it was for probabilities, you will then check whether it is equals to 1, which is the probabilities when added together, okay? If it's not the same number, then you'll write the difference on the outside, all right? We are moving on. Let's look at a worked example for Venn diagrams with 3 sets, all right? Let's check here how we can work with this. Out of 250 learners in a school, all 23 wrote one or more of business studies, geography, and science. All right. If we let business studies be denoted by B, geography be denoted by G, and science be denoted by S. All right. Let's check now. 91 wrote business studies, 120 wrote geography, 154 wrote biology. Remember the APO, all right? 77 wrote geography and science, 67 wrote geography, science but not geography or business studies, 40 wrote all 3. You see, that is where the APO starts. Okay, all 3. But you can see here, all but 23, which means that wrote one of the following. It means there are 23 that did not participate. So we can always also fill that one out, okay? There are 23 out of 250, which means we expect around 250 minus 23 here. We expect around 227. We expect 227 to be in our 3 given sets, all right? Draw a Venn diagram to represent the information. Determine the probability that the learner selected at random from the sample wrote geography only, wrote business studies and science, but not geography, does not write geography or science, all right? Okay, fine. Now, let's check how we can do this, okay? We're starting with the Venn diagram. They said 250 learners. I did put the 250 as the number of elements in the sample space. All but 23, which means we need the 23 outside, all right? Now, if you check here, we've animated it. The 23 comes on the outside. And then from there, usually when we follow the APO methodology, we are starting with all. You can see here there is all. 40 wrote all. So we need to start with the 40 as the overall intersection. There it comes through there, all right? And then from there, we need to look at what? The pair. So the pair is here, here, and there. Those are the pairs. So we need to check here the pairs here, all right? Let's check the first one. It says 77. We are done with this one. We are done with that. It says 77 wrote geography and science. So if you check geography and science. All right, this is geography and science. The total should be 77. If you add 40 and 37, 77. They gave us 77, but we've already counted 40 of those. So we'll say 77 minus 40, which gives us 37. All right, moving on. It says now 51 wrote business studies and geography. 51 for business studies and geography. It should be 51. We've already counted 40, so we'll say 51 minus 40, we get 11, which will look at business studies and geography only. All right, and then from there, moving right along, we get that now out of these we can see that 120 wrote geography. 120 wrote geography, which means everything here, when you add it, you are going to get 120 on the circle of geography. So you'll say 120, subtract 11, subtract 40, subtract 37, so that you can know what is outside there. All right, moving on again, it says 67 wrote science, but not geography or business studies. So these ones, you can see that they wrote science only. This is science only, all right? Science only, because it says they wrote 67 wrote science, but not geography or business studies. So that is why we put that 67 unaltered there, all right? And then from there, we move on. It says 154 wrote science, all right? So out of 154, we are going to subtract 10, 40, and 37. We get 67, all right? And then we are left with 91 that wrote business studies. So out of 91, we subtract 11, 40, and 10. So the difference there would be 30. So that would complete our Venn diagram. So you can see in this Venn diagram that the events are not exhaustive because there's 23 elements that are outside of the events, all right? Now, determine the probability that a learner selected at random from the sample wrote geography only, wrote business studies and science, but not geography, that does not write geography or science. So what we need to do here is we bring back our Venn diagram, all right? We bring back our Venn diagram, and then from the Venn diagram, we can now answer the questions. Geography only. Geography only should be this. 32 represents geography only, because once you start tapping into this, this is geography and business. This is all three: geography, business, and science. This is geography and science. So you only want geography. So you can see it is 32 upon 250. As a simplified fraction, it is 16 divided by 125. So usually you get that this would just carry that solitary mark there. And then from there, wrote business studies and science, but not geography. Business studies and science, but not geography. Business studies, there is business, there is science, there is the combination of business studies and science, but not geography, all right? So this is business studies only, we exclude this one. This is science only, we exclude this one, but business studies and science, but not geography, which means if they just said business studies and science, we're going to take everything here. But they said, but not geography, and this 40 includes geography. So this is 10 over 250, which is 1 divided by 25. The last one did not write geography or science. Did not write geography or science. So geography and science should be out, all right? So what do we do here? We are going to take business, all right? And then we are going to take this one, which is 53 over 250. Because they said geography, all right, does not write geography or science, all right? Did not write geography or science, which means the learner wrote business or did not write anything. All right. So alternatively, you can also use here the probability of not geography or science. Okay, this would be equals to 1 minus the probability of geography or science. All right. So you are going to perform the calculation that way. All right. That's an alternative. That's an alternative. So that's how you work with a Venn diagram with 3 sets. All right. Let's go back. So that's how you work around the Venn diagram with 3 sets. Now I want to give you an activity where you are going to also play around Venn diagrams with 3 sets, but it is a more interesting activity because of the existence of the unknowns there. So we are on activity number 1. I am going to give you just 8 minutes to complete all the questions in this activity. Just 8 minutes, all right? And your 8 minutes time starts now. Right, hello and welcome back. I hope you were able to solve the problem. All right, let's go through the solutions and see how you were supposed to work around it. Okay. A school organized a camp for their 103 grade 12 learners. The learners were asked to indicate their food preferences for the camp. They had to choose from chicken, vegetable, and fish. The following information was collected. 2 learners do not eat chicken, fish, or vegetable. So you can see the 2 here. They should lie outside. They are still in the camp, but they do not prefer any of these. They do not eat any of these 3 choices. 5 learners eat only vegetables. So you can see they've used the word only there. 2 learners eat only chicken. They've used the word only there, so you can just fit it straight to the Venn diagram. 21 learners do not eat fish. So if they say 21 do not eat fish, then it means that they eat chicken, vegetable, or they are outside. Okay. And then 3 learners eat fish only. Okay, so 3 will only eat fish. You can fit that into the outside into the individual, okay, because we are using that APO there. All right. 75 learners eat vegetable and fish, so this is the intersection, or it's the pair. All right. So that's where you need to also remove the intersection of all 3. All right. Let the number of learners who eat chicken, vegetable, and fish be denoted by X. All right. So let those be denoted by X. Sometimes they don't tell you should denote them by X, but they just say they are unknown. So you can use any letter there to represent the unknown that you can solve for. All right, draw a Venn diagram. Okay, now let's start. We start with the 2 learners, all right, because they are outside there and it was explicitly stated in the statement there. All right, and then from there we can look at the 5 that eat only. We can look at the only ones. All right, 5 only. So those are the outside, or the individual. All right. But now, because we are certain about them, we can fit them in, all right? And then we have 2, all right, that eat only chicken, and we have 3 that eat only fish, all right? And then from there, we can look at the overall, the X learners that are eating all 3. All right, then we can then look at the end. All right, let's see. 66 learners eat chicken and fish. So for chicken and fish, it is 66 learners. All right, it is 66 learners. So what do we do there? We are going to actually take away we are going to take away X from the 66, because 66 eat chicken and fish. So chicken and fish is this. So in total we must have 66, but we've already counted X, so that is why we use 66 minus X. All right, and then we've done that, and then from there we have 75 eat vegetable and fish. Vegetable and fish is this. All right, is this. All right, but we've already counted X there, so it's 75 minus X. We've dealt with that, so we are only left with this one. 21 learners do not eat fish, so it will allow us to fit in the space, because if 21 do not eat fish, all right, if 21 do not eat fish, then we can use the difference, because the number of learners that do not eat fish is these ones, and these ones. All right, so all of them should add to 21, including these ones. All right, so all of them should add to 21. So you have 21, and then you subtract 9 from 21. All right, so you must be left with 12. That is why we fit in 12 there. All right, That is why we fit in 12. So the Venn diagram is complete. The Venn diagram is complete, all right? Let's move on. Calculate x. Okay, let's bring in our Venn diagram here. And to calculate x, what we can do is we can add everything here. We add everything here. Then we know it's going to sum up to 103. All right. So when we add everything, we say it will add up to 103. So it's 5 plus 12, 5 plus 12 plus 2 plus x plus 75 minus x plus 66 minus x plus 3 plus 2. That should be 103. And then we solve for x. In doing so, we get that x is equals to 62. All right, x is equals to 62. So we can change this Venn diagram and substitute where we see x, we put 62. So this would be a Venn diagram that we can use for the calculations there. All right. So determine the probability that a learner chosen at random eat only 2 of the given food choices. All right. For only 2, we have 12, we have 4, we have 13. All right. And then this would be the case there. Let me bring in the Venn diagram, all right? It was supposed to come first, all right? So we are saying if this is 66 minus x, we got that x is 62, all right? We got that x is 60. Let me check again. We got that x is 62, yes. So it will mean that now this would be 66 minus 62, which is 4. And then this would be 62. And this would be 65 minus x, 75 minus 62. And that would be here, this would be 13. And then from there we are saying we'll eat only 2 of the given food choices. Only 2, that should be 12. That should be 4, that should be 13. So that's 12, that's 4, that's 13. That is only 2. And then divide by the total, which is 103. That simplifies to 29 divided by 103. All right. Moving on. We now get into a new concept, a concept of independent events, all right? A concept of independent events. We are saying 2 successive events, A and B, are independent if the outcome of the first event does not influence the outcome of the second event. This means that the probability of the first event is not influenced by whether the second event occurs or not, all right? There are events, these are events that can happen simultaneously. They can all happen at the same time. If 2 events are independent, then the following rule applies. This is the product rule, all right? Probability of A and B is the probability of A times the probability of B. So this is the product rule for what? For independent events, all right? This is the product rule for independent events. Now let's look at independent events versus mutually exclusive events, all right? Independent events versus mutually exclusive events. Please do not confuse independent events with mutually exclusive events. They are completely different concepts. If 2 events are independent, they cannot be mutually exclusive. Because remember, if they are independent, we are saying the intersection exists, all right? The intersection exists, but with mutually exclusive, we said the intersection is 0. Independent events will always have an intersection, whereas mutually exclusive events do not have an intersection, all right? So consider the following table, which summarizes the difference between the 2. The probability of A and B in mutually exclusive events is 0. But in independent events, the probability of A and B is the probability of A times the probability of B. All right? What about the addition rule? The probability of A or B is probability of A plus the probability of B if they are mutually exclusive, because the intersection is 0. But in independent events, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B, which can also be written this way: probability of A plus the probability of B minus the probability of A times the probability of B, because that's what probability of A and B is. So that is why sometimes they refer to this as the sum minus what? The product. That would be for independent events, all right? Sum minus the product of the probabilities of the two events, all right? Now let us look at the dependent events, which I normally I don't like using the word dependent. Usually I use not independent, okay? Not independent, because it does not mean that if events are not independent, then they are dependent. Getting into dependent events would need us to dive deep into the concepts of conditional probability, which is not part and parcel of your CAPS curriculum, all right? So two successive events are not independent if the first outcome, all right, or if the outcomes of the first event do have an influence on the outcome of the second event. Let's take an example. I have a very nice lunchbox there, all right? I hope you are not hungry, okay? Because you'll want to have some food there, food items from my lunchbox there, all right? So it contains sandwiches, grapes, and nuts, all right? So event A is picking a food item and eating it, all right? Event B is picking another food item and eating it, all right? Clearly, the two events, event B depends on what happened in event A. If on the first output you took a food item, let's say you took grapes, you ate grapes, all right? If you go again, the grapes will no longer be there because you've consumed them, all right? So we are saying that what happens, event B, the outcomes of event B are influenced by the outcome of what? Of event A, on what happened in event A, all right? So that is why we say they are not independent. They are not independent. And then example 2 that you can use, picking a ball from a jar without replacing. If you pick a ball from a jar here, you had 4 balls, you pick one, you do not replace. When you go back and want to pick another one, you will now be choosing from 3 balls as opposed to be choosing from 4. So going there for the second time depends on what happened when you went for the first time, all right? So we can move on with a worked example. We are now looking at the terminology here. Let's see examples that deal with the use of terminology and equations. If events A and B are two independent, here it's very, very important that you highlight the key words, all right, as you have studied them in probability. They are two independent events. What do you know if events are independent? Probability of A and B should be the probability of A times the probability of B. That is what you know, all right? And then probability of A is given and probability of B is given. And they say determine the probability of A or B. You know A or B, you can determine it using the general addition rule. The probability of A plus the probability of B minus the probability of A and B. If they were mutually exclusive, the probability of A and B would be 0. But because they are independent, the probability of A and B would be given as the product. All right, as the product. So let's check here how we can solve this one. All right, now start with the probability. This is for what? For the fact that they said the events are independent. All right, and then we calculate the probability of A and B. We are given that of A and that of B. We get the probability of A and B as 0,3. All right. But remember, the question wants the probability of A or B. So we use the general addition rule to do that. Now we have the probability of A, we have that of B. We've just calculated that of the intersection. So we can just substitute. All right, 0.6 plus 0.5 minus 0.3, and then we get that the probability of A or B is 0.8. All right, 0.8. Okay. Now we have an activity 2. I am going to give you, to look at this, I'm just going to give you 4 minutes, all right? 4 minutes to work through activity number 2, all right? And your 4 minutes time starts now. All right, hello and welcome back. Okay, let's go through this problem and see how you were supposed to solve it. Remember, we are available on our WhatsApp interactive line. I think it's at the bottom of your screen. It has just popped up, 079-573-2908. Please do ask questions based on today's lesson so that we can be able to assist you. All right. Events A and B are such that probability of A is 0.5, probability of not B. You see now, they are talking about now the complementary rule. We know probability of B plus the probability of not B is equals to 1. All right, and then probability of A or B is 0.8. Are events A and B independent? So we want to know whether they are independent. So we want to know whether the probability of A and B is it equals to the probability of A times the probability of B. We want to know whether the probability of the intersection is equals to the probability of the product of the two defined events. So we want to know whether the probability of the intersection of the two events is equals to the probability of the product of the individual events there. So that's what we want to find out. Okay, so but first things first, we must sort out this not B issue so that we have the probability of B. Because in the equations, for you to get PA and B, we need PA and PB, not P, not B. All right? So that's not what we need. So let's look at the solution sets there. We start by sorting that issue out. The probability of B now becomes what? 1 minus the probability of not B. So if you do that, you get that the probability of B is 0.7. Now you have the probability of A, which is 0.5. You have the probability of B, which is 0.7. Now you can determine that you also have the probability of A or B as 0.8. So you can determine the probability of A and B using the addition rule, because you do have the probability of A or B, you have that of A, you have that of B. So you can work out the probability of A and B, you get that it is 0.4, all right? The probability of A and B is 0.4. So you've done this part here. Now you want to check it against, you've done this one, you want to check it against that, the product, okay? So what do we do then? We are going to look at the probability of the product. Probability of A and B would be equals to 0.5 times 0.7, which is 0.35. Then we compare the two. Correct to 2 decimal places, because that is what the instruction says in our instruction page. Round off your numerical values to 2 decimal places unless otherwise stated. Please do not take the instructions for granted, all right? Do not take them for granted. All right, so now, because we've compared the two, we can see that the probability of A and B is not equals to the probability of A times the probability of B. As a result, the two events are not independent. All right, they are not independent. This is a skill you need to know, because usually in our contingency tables, that's what the contingency tables do. All right, the contingency tables, they are going to help us in checking whether events are mutually exclusive or not, and also to check whether events are independent or not. That is what the tables will do for us. All right, but the 3 diagrams, they're going to help us with the complementary events. All right, they help us to analyze events that are complementary. All right, those are events that are mutually exclusive and exhaustive. Let's look at the tree diagrams. All right, a tree diagram is a tool that we use in probability that allows us to calculate the number of possible outcomes of an event, as well as to list those possible outcomes in an organized manner. All right. So if you want the number of possible outcomes and to list them in an organized manner, we use the tree diagram. That is why when we introduce the fundamental counting principle in grade 12, we use the tree diagrams because it shows us those outcomes in an organized manner. All right. Now, a tree diagram is used when dealing with complementary events. Those are events that are mutually exclusive and exhaustive. A tree diagram will have a branch with the probability of each branch written on the branch and the outcome written at the end of the branch. This can be illustrated below using a toss of a coin. All right. If you toss a coin, this would be the branches. All right. This would be the probability written in the branch, and the outcomes are either head or tail. All right. That is a basic tree diagram. All right. Let's get into it now. Looking at worked example, a bag contains 3 balls, green balls. All right. That is our bag, and 4 white balls. It's green, 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 white, 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 white. All right. 2 balls are taken at random from the bag, one after the other. That's what happens in tree diagrams. When an experiment is carried out, the other one is carried out after the other one. You don't do everything at the same time. Replacing, this is important, the first ball before the second one is drawn. So there is replacement. Draw a tree diagram listing all possible outcomes. All right. Let's check here. Let's look at our tree diagram. We have 2 outcomes, possibilities. It's either it's green or white. So we can have the branches for green and a branch for white. But we don't do it once, we do it twice. So for the second draw, we would have, if the first one was green, the second one may be green or white. If the first one was white, the second one may be green or white. So if you move along the branch, you can get the possible outcomes as GG, GW. This means G and G, all right? And then GW means G and W, all right? G and white and green, all right? White and white, all right? So now let's fill in those outcomes. How many green balls do we have? 1, 2, 3. Green is 3, white is 4. A total of 7 balls. So what is the probability that a ball is green? It should be 3 divided by 7, all right? Put that in there, 3 divided by 7. What about white? It's 4 divided by 7, all right? For the second draw, because you replaced the ball, for the second draw, it would be 3 still for green and 7 in total. For probability of drawing a white is still 4 out of 7. If the first one was white, the probability that the second one would be green, it's 3 upon 7. If the first ball was white, the probability that the second one will also be white is 4 upon 7. Now, we can multiply. Along the branches, we multiply. All right? Along the branches, we multiply those probabilities. So we can multiply there and get the probabilities for each sub-branches there. All right? Now, let's answer the questions. Determine the probability that both balls are green. If they are both green, all right, we are looking for what? The probability of green and green, or GG. Already we have the answer here, all right? Already we have the answer there. G and G, that is 9 over 49. The first one is white and the second one is green. The first one is white. All right, the first one is white and the second one is green. So you are looking for the probability of W and G. All right, so we are looking at this. The first one is white, the second one is green. That is the outcome. There, we've already worked it out. So that's what we get. Probability of green on white, we get 3 over 4 over 7 times 3 over 7, which is 12 over 49, all right? That is when replacement are done. Suppose that there is no replacement. Without replacement, it was still green balls are still 4 or no 3. Green balls are still 3. White balls are 4. In total, you have 7. I want you to try this one out, all right? I am just going to give you 4 minutes to work on that. Just 4 minutes to work on that. It's a similar problem, but now the catch here is without replacing. Your 4 minutes time starts now. Right, hello and welcome back. Let's get to the conclusion of our lesson, all right? Let's see how best we can analyze this. we have 3 green, 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 and 4 white, 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 white. Okay, let's analyze this. Now it is without replacing. So after you've taken a ball out, it is not replaced. So we need to be smart about this. All right. Now let's check. Obviously, it's the same problem that we've analyzed before. So this structure, or the skeletal structure of the tree diagram looks the same. Okay, it is only now the probabilities. Now let's check. When you start, the probability of drawing a green ball should be 3 divided by 7, because there are 3 green balls out of a total of 7. For white, it would be 4 divided by 7. Now, it's important to also note here that the sub branches will always give you the probability which is equals to 1. All right, just want to take you back. Okay, just want to take you back. Even here, the sub branches will always give you a probability of 1 when you add. All right, when you add along the 2 sub branches, you'll always get the probability which is equals to 1. So also here, because we are talking complementary, we say tree diagram is very nice when dealing with complementary events. So when you add these, you get 1. Now, you want to know what would happen on the second draw. So it depends on what happened on the first draw. So if the first ball was green, it means that now you have 1 less green ball. So you now have 2 green, 4 white, which makes a total of 6. All right. So what is the probability that the second one would be green? It will be 2 divided by 6. But for it to be white, you still have 4 white balls. So it will be 4 divided by 6. But if you add the 2, you still get 1. If you add these probabilities, you still get 1. All right. But if the first ball was, remember, originally you have 3 green, 4 white is 4, which is 7. If the first ball was white, it means the white balls are now 3, the green balls also 3, the total is 6. So if the second ball, the probability of throwing the second ball being green, it will be 3. You had 3 green balls remaining, 3 divided by 6. The sample space is reduced by 1 because you did not replace. And then for it to be white, it will still be 3 over 6 because remember on the first draw, the ball was white and it was not replaced. So you are left with just 6. So still if you add these 2, you are still going to get 1. So we go to the outcomes. As we did previously, we multiply along the branches. We are going to multiply, all right? Along the branches, we multiply. So that's what we get as our outcomes. And then determine the probability that both balls are of the same color, all right? For them to be of the same color, they should both be green and both be white. So you see, the answer is either here or there. So because of that, because you are getting answers from 2 different outcomes, you are going to add the answers. If we move along the branches, we were multiplying. But if we get answers from different outcomes in that column there, we add, because now we are looking for probability of green and green, or what you call white and white, which would be the probability of green and green plus the probability of white, white and white. So when you want to do that, there we go, of the same color, it's either they are both green or they are both white. You can take the probabilities for the both green and probabilities for both white, all right? And then you get the answer. For them to be of the same color, the probability would be 3 divided by 7, all right? Now, let's go to the last part of our lesson, which would be the contingency tables, all right? The two-way tables are used or are useful for representing multiple outcomes and determining the probabilities of certain events. Two-way does not necessarily mean the column must have 2 rows and 2 columns. Two-way means it can be a 2 by 2, a 3 by 2, and a 5 by 4, etc., depending on the number of rows and the number of columns. All right. Now, contingency tables are useful when determining whether events are independent or not, and when determining whether events are mutually exclusive or not. That's what a contingency tables are for. Right, I have an example. We'll go through the example together. The table summarizes the participation in sport among 98 boys and girls at a school. So total is 98. Okay, a person is chosen at random. Determine the probability that a person is a boy. So we are going to be looking at boys here. You can see the total for boys is 40 over the overall total, which is 98. So the probability that is a boy is 40 over 98, which is 20 over 49. All right. The person doesn't play sport, okay? We see this is doesn't play sport. They did not specify the gender. So we are going to be looking at doesn't play sport. You can see the total here for those that do not play sport is 23, all right? So we are going to be taking doesn't play sport as what? As 23 divided by 98, all right? And then from there, up next, determine the probability that a person is a girl who plays sport. Is a girl who plays sport. So now we are looking at the intersection between what? Between a girl, all right, and what? And play sport. Where girl meets play sport, okay? So we want the number of girls that play sport. So we are looking at this particular intersection, the number of girls that play sport, all right? So we're going to have that this would be 43 divided by 98 because these are the girls that play sport, okay? And then the person is a boy who doesn't play sport. We are looking at boys, all right? We are looking at boys, the intersection between a boy and doesn't play sport. So we are looking at 8 individuals here, all right? So the probability will then be 8 divided by 98. As a simplified fraction, it's 4 divided by 49, all right? And then from there, we move on to the summary. I think we've completed our work here on the contingency tables, which means that you should take this a step further and look at contingency tables where you prove whether events are independent or not, and where you prove whether events are mutually exclusive or not. Even with the tree diagrams, you should also be looking at tree diagrams with conditional outcomes, all right? Please look at those concepts. They're very, very important as well. All right, let's summarize what we've worked on today. We said probability is the likelihood of an event occurring, all right? And then we looked at independent events. We said the occurrence of one event does not affect the occurrence of the next, all right? And then we used the product rule for that. We spoke of mutually exclusive events as events that do not occur at the same time, and we said we can use the rule, the general addition rule, but for mutually exclusive, we know that probability of A and B, all right, is equals to what? 0, all right? So we can adapt the probability rule or the general addition law. Venn diagrams, tree diagrams, and contingency tables are used. These are the tools that we use. We use the Venn diagrams with 3 sets. That is what we are interested in grade 11. We use tree diagrams, contingency tables as a way of representing probability of specific outcomes. We said probability is expressible as a fraction or a decimal, all right? Or even a percentage, or even a percentage. If it's a percentage, it is trapped between 0 and what? And 100%. If it is a decimal, it should be between 0 and 1, all right? That's what we have there. And then now, the next lesson, please join us next week on the 20th from 2:30 to 4 o'clock. We'll be looking at the fundamental counting principles and all the concepts that are involved in the counting principle. Please do make sure that you join us, all right? So For today, we are done. Thank you so much for tuning in. Please take care of yourselves and take care of each other and practice mathematics. Goodbye.